Hello everyone, welcome to this video tutorial. In this video, we will learn how to perform transient simulation of an induction motor using the ANSYS Simplorer software. So in this video, I am going to use the lumped parameter model of induction motor, the model that is available here, basic elements, circuit, electric machines. Yes, the model of the electric machines available here. In the previous videos, we used the lumped parameter model of a DC machine. So let's do the simulation using this model. And in the next videos, I will use the finite element model. Yes. So this is the finite element model of the induction motor. And in the next videos, we will learn how to link the finite element model to the Simplorer. Okay. So it's good if we try the circuit first with the available lumped parameter models, and when everything is okay, we can replace the lumped parameter model with the finite element model. So anyway, here I insert a new Simplorer design, and from here basic elements, circuit, electric machines, induction machine. We have two items here, the induction machine and the slip ring induction machine. I'm going to use this one, the squirrel cage induction motor. So when you place an element here in the design area, you can right click and click on this option here, component help. So you can find the information regarding this element and an example that is here. So you can see the modeling procedure, voltage equations, yes, in 2-axis reference frame, and this is the torque equation, the mechanical equation, and the transformation that we have. So here we placed this element, and as you can see, we have the phase A, B, and C, and one mechanical port. First, let's set the parameters of the motor. Here I have a 1 HP induction motor, and I perform the finite element simulations. The videos are available in the induction motor design course. So if you are interested, you can refer to those videos and learn how to calculate the equivalent circuit parameters of an induction motor using the finite element method. So I am going to use this benchmark induction motor. Let's set the parameters. The number of poles is 4, and so the number of pole pairs is 2. The moment of inertia is 0.0017, the example that we considered in the previous videos. The main inductance, the mutual inductance or the main inductance, is equal to 0.613. So 0.613. You know that what is the main inductance? Yes. Here you can see the equations for inductance in 2-axis reference frame. So here you can see the alpha and beta. These are for the stator and these are for the rotor. Two-phase formulation, not three-phase formulation. Yes, two-axis reference frame instead of three-axis reference frame. So here we have L1, that is the leakage inductance of the stator. Lm, mutual inductance. L2 is the leakage inductance of the rotor. So here, what is the stator resistance? The stator resistance is 15.7. The stator leakage inductance, the summation of the leakage inductances is 0.053 Henry. So I'm going to consider equal values for the stator and rotor leakage inductances. So this is 0.053 divided by 2. And the same thing for the rotor leakage inductance. What is the value of the rotor resistance? 8.4. This is an induction motor with a squirrel cage. Yes. So this is the equivalent phase resistance for the rotor cage. We discussed this concept in the induction motor design course. So this is 8.4, this number that we have, and that's all. These are initial values for the currents and initial rotor position and rotor speed. 0 for all, and I can press OK. So now I should feed the motor using a three-phase source. Like this model, I can consider E1, E2, E3, or simply I can search for a three-phase source and use this three-phase source that we have here. Yes, so source, a three-phase source. You can set the line parameters. So you can check these inputs in the help, the line resistance, line inductance, resistance to neutral point, and inductance to neutral point. I consider the default values here. Just I set the amplitude of the voltage, that is 328. This is the amplitude of the phase voltage, I think. So let's check. Where is the amplitude? This is the source amplitude, source frequency. We can check by measuring the input voltage. You know, the line to line voltage of this induction motor is 400 volt. So we can measure the value here. So let's consider 50 Hertz frequency, the voltage of the phase A, phase B, and finally phase C, and connect the N to the ground. Now I should consider the load torque. Yes. So here we input the moment of inertia. So in this model, actually we have this element. So where is the physical domains? Mechanical velocity formulation. We have this element inside this object. Yes. So actually we have a circuit like this, a mechanical circuit. We discussed mechanical circuit in the previous video. This is the electric torque generated by motor, and this is actually the rotating element. Okay, so we should add the load torque also, that is in this direction. So here I add a torque source, rotational torque source from this representation, velocity force representation. You can check the information regarding this, what kind of elements we should use in this simulation when we are going to use this lumped parameter model. Okay, so you can check the type of the torque source. So I don't need this element, and I just add this torque source element. What should be the direction? In opposite direction of the electric torque. So I can add the ground here, and that's all. Also, I should consider the friction loss. Yes, I should consider the friction loss. I will explain it later. Here, I'm going to set the value of load torque equal to 0. Yes. First, I am going to do the no load simulation. Just apply the rated voltage when there is no load torque. And also let's measure the voltage. Okay, voltage between 2 points between the phase B and phase A, just to check the line to line voltage. Yes. Anyway, so let's set the simulation time. I'm going to consider 0.3 second, and these are okay. Yes. So we can run the simulation. So simulation completed. Now we can plot the angular speed im1.n, that is the rotor speed in RPM. Yes, you can see the oscillations overshoot, and finally we have this speed, yes, equal to the synchronous speed, because we don't have any load. So if I consider 1 second and run the simulation again, so you can see the waveform here, the speed waveform. The steady state speed is equal to 1500 RPM, equal to the synchronous speed. Also, let's plot the Vm1.V input voltage. So if I calculate the RMS value of this waveform, RMS 400 volts. That is okay. The number here is the amplitude of the phase voltage. So let's delete this element. We don't need that. Just I wanted to check what is the variable that we have here. This is the amplitude of the phase voltage. And here let's plot the current of the phase A, B, and C. The stator winding currents, you can calculate the RMS value of the current, the phase current, for the last electric period. Calculate for the last electric period and specify the time range here, right? For the last electric period. The value of no load current is 1.2 amps. So, the rated load torque of this motor is 5.1 Newton meter. And for this rated torque, the RMS value of the current should be equal to 1.88, close to this number. So let's set the load torque and repeat the simulation again. This is the motor speed. The rated one is lower than the synchronous speed, yes, because we have a slip. And what is the average value for the last electric period? Should be close to 1400 RPM. This number. This is the rated speed that we have when we apply the full load torque. Yes, you can see the waveform of the electric torque also, the IM1, the electric torque waveform. We have the startup, and this is the steady state torque profile. What is the RMS value of the current? 1.73. Okay, that is fine. So, yes, here we considered a load torque. The direction of the load torque is in this direction to the mechanical ground, so in opposite direction of the electric torque. Yes, you can check the reference here also, the reference example that we have, and we applied the three-phase source, the input voltage, right? This is a line start induction motor. So how I can include the friction coefficient? You know, in ANSYS Maxwell, when you have the finite element model of an electric motor and you define the motion band, the rotating elements, here you set the moment of inertia and damping and the load torque equation. So how we can consider the damping in this model? I can consider a damper element. So this is the rotational damper. So rotate, and here we can set the value. Here the damping coefficient is equal to this number that I have here. This Excel file is for design of induction motors. Okay, you can check the corresponding videos in the induction motor design course. So let's copy and paste this number here. This is the direction of the torque, and rerun the simulation. So this is the speed this is the value of the phase current and mechanical torque that we have. Its value is a little bit higher than 5.1 because we added the damping to the mechanical equation of this motor that we have. Also, you can measure the value of the electric torque, yes, in different parts of this mechanical circuit. Okay, anyway, in this video, just I wanted to explain the procedure for simulation of the induction motor, the transient simulation, no load simulation by using the lumped parameter model. And in the next video, we will replace this model by the finite element model and compare the results. Thanks for watching.